Welcome to the last talk. As you can see, I have 62 slides, so who's still ready? No, I'm making it a little bit faster. So thanks a lot for inviting me to this talk. It's actually the fourth time I'm giving this talk. The last time was it was at midnight on the main stage of 38th C3, so the Chaos Communication Congress in Hamburg. And very happy to bring some updates today to the 100th Datageeks Meetup. So I joined the community some years ago. I think this is my 32nd Datageeks Meetup. And the last time I presented was actually also at Allianz, right? And the last time, Allianz, they had a talk on life insurance, and I said, I have life insurance with Allianz. And this time there's a talk on pet insurance with Allianz. And I also have pet insurance with Allianz, right? So thanks for the changes you implemented. It's really nice for me as a pet owner. Yeah? Awesome. So my talk is called Competitive Time Trial AI for Need for Speed Most Wanted, using deep reinforcement learning. So quick question, who has played this game actually? Yeah, half the room, nice. So when the game was released, I was 17 years old, right? And I invite you to travel back in time with me because 15 years ago, I was a pro gaming athlete for Need for Speed. I played Need for Speed Most Wanted, Need for Speed Carbon, Pro Street, and Shift. I was part of Team Alternate. Team Alternate was one of the biggest teams at the time for esports in Germany and the best Need for Speed team that we had in Germany. If you don't recognize, I'm this person here. And I swear I'm not high on this picture. It's just unfortunate conditions. But this was an autograph card that we had and we gave away. I think I signed 3 autograph cards at Games Convention 2006 in Leipzig. But it was a great time at the time for Team Alternate. And at the time, so I was playing very competitively, and Need for Speed Most Wanted is an arcade racing game. It's the best-selling game of the whole franchise, with 16 million copies sold. Actually, the German Wikipedia says 16 million, the English Wikipedia says 18 million, so don't know which number is right. And it was a popular esports title at the time. It was played at the Electronic Sports League, where I mainly competed, and the World Cyber Games, which were kind of the Olympics for video games at the time. It's played in races on circuits in 1 versus 1 mode. You usually do 5 to 6 laps, and the first one to complete the distance, of course, wins. Very simple. And in most leagues, all of the tuning parts are allowed. Just by WCG rules, the Junkman parts were not allowed. Junkman parts are kind of special tuning parts. You could cheat with these, so they were not allowed with WCG rules. All cars were allowed, so the best cars were the Lotus Elise, because it was had a nimble handling and was fast around the corners, and the Porsche Carrera GT for ESL rules because it has raw power and it's just super fast in the game. In this talk I'm going to focus on the first one because it's my favorite car and I used it for most of the tracks in Most Wanted by ESL rules. So NOS, so Turbo Boost, was disabled in both leagues, and Collision were also disabled. NOS was disabled because you could cheat with that, like infinite NOS hacks or stuff like that, and collisions were disabled because the netcode was quite bad. So this game was released in 2005, and it's unthinkable today, but some people still had ESDN connections at the time to play against, so it was quite a challenge to get that going with collisions, so these were disabled. Yeah, and at the time, I was pretty good. I was in this pro gaming team, and I still own a world record on one lap for Heritage Heights, and that's a lap that I uploaded on YouTube 16 years ago. And I'm just going to play it to you and walk you through the lap so you have a means of comparison for what's going to follow. Hope it works now. Let's go back to the beginning. Yeah, team logo, of course. Yeah. So the lap time is a 1 minute, 6 seconds, and 85 of a second, so you can remember that already. And now we get into it, and the lap starts right now, and the easy part is fast. You just full throttle, then you keep it nice and tidy here, keep the inside line, you don't crash into the toll booths here that are appearing. Then this part is easy, it's really full throttle. You go on the left-hand side to the tunnel, then you cross over to the right-hand side here. Then there comes some S-curves, it's a difficult part. You brake, turn left, turn right, turn left again. Don't hit anything, otherwise you will lose time. Keep it nice and tidy here. Just choose the optimal line, go through this little, under this little bridge. Then here I go to the very right, then to the very left, to the very right. Brake a little bit, go through the underpass, don't hit anything. On the jump you need to keep it straight, otherwise you will lose time. cross over to the left-hand side, continue straight on, keep the steering very straight, otherwise you will bounce off and lose time. This one is easy, full throttle. On this part, you lift a little bit because you have these cornerstones from the sidewalk, and you can slip away on this. Don't hit any of the garbage here, and then cross over to the start-finish line, and then boom, you have a world record, 1 minute, 6 seconds, 85. Yeah? Good. And then, my career transformed from being a data scientist when I came to the first Munich Datageeks meetup to now being head of data and AI for E.ON. But in my free time, I still like to spend time on programming stuff. This was all before vibe coding and coding assistance, so I started with this project end of 2022. No GPT around at the time, not really. And then Sony has released this paper and was published on Nature magazine on the cover. So the second one, which was called Outracing Champion Gran Turismo Drivers with Deep Reinforcement Learning. And there's also a predecessor to the paper. That's the first one here, Superhuman Performance in Gran Turismo Sport using Deep Reinforcement Learning. My talk focuses more on the first paper, and I saw this paper and I was like, yeah, you wanted to do this for a long time, so if Sony can do that, how hard can it be? And then I embarked on a journey, which is still keeping me busy today. So I wanted to implement that, what Sony did, because I said, I have the knowledge, I have the save game still. I saved the save game for the last 20 years on this game, and I still have my setups and my cars and everything. And I said, let's kick it off, let's get it going. But there was a problem. So there's no game API, there's no code from the Sony paper, so it was a start from scratch. I needed to do everything. And what I did is I created a custom gym environment. So nowadays OpenAI is famous for GPT and ChatGPT, but back in the days they were famous for their reinforcement learning gym environment. So I implemented a gym environment for reinforcement learning in real time. Most of the things you do with the Atari games are not in real time. You can run them as fast or slow as you want. But this one runs in real time because their game runs in real time and I have no means to control it. And implement that and essentially define 4 parts, an action that you can give into the game. I'll explain that later. An observation vector, which is basically a LiDAR in the GPS system that I implemented, a reward function, and a done indicator that indicates when an episode is done. Typically an episode is done when a lab is completed or time limit is reached. Second thing is I had no API. Even if you were thinking about training it on images from the game, which is theoretically possible, but quite slow if you do it in Python, and I want to do it in real time. So I want to do 30 gradient steps per second. If I were to do that on images, even if I scale down to the lowest resolution, transforming an image to grayscale even takes 10 milliseconds or 12, and I have maximum 8. So that was a challenge if I want to do a gradient step on top of that. So I needed to hack the game for an API, and what I did is I checked the game's memory and got the variables out of the game's memory because I can read that in nanoseconds. Yeah, then I needed to steer, so I gave the agent a virtual gamepad, a virtual Xbox 360 gamepad with the regamepad library that's available. Later on, I man-in-the-middle attacked the game and directly wrote the steering commands to the game, so I don't need a driver for that. And in the end, then I trained the agent using the soft actor critic algorithm, the same one that Sony used, using stable baselines free package in Python because it has stable baselines, because getting reinforcement learning right is a really difficult task and getting it stable. Yeah, so if you look at that chart here, you start on the left-hand side, so I have this, now the agent term is very popular, back in the days it was not, but you have a deep reinforcement learning agent abstracted by the stable baselines package. This agent can take an action, so that's like steering or braking or throttling, and gives this action back to the environment, which is abstracted by the gym environment and the Need for Speed Most Wanted API that I created. And this in turn returns a reward, an observation, and a done indicator. So that's it. Okay, some formulas. I know it's already late. Just one slide with a little bit of formulas to understand what's really going on. So what the soft actor critic really tries to do is the target is to maximize the sum of all rewards plus an entropy term for exploration. So there's a trade-off between exploitation, getting faster, gaining more rewards, and exploration, trying new things out. Both is important. So here the R is the rewards and the H term is the entropy, and alpha is the entropy coefficient, where you can steer how important the trade-off is between exploitation and exploration. Good, so I want to maximize this term and find the right policy or the right actor that does that. What's an actor, what's a policy? So the policy for each action given the state is characterized by the observation, given by the state characterized by the observation, and pi theta is the actor, parameterized by parameters theta, is a distribution function over all possible, over the actions given the state S. So this one is the right one I want to find. So actually that's the driver. You know, given each state, each observation, it outputs the correct action. And then in the soft actor critic, you have the critic. The critic is kind of the co-driver, and it's a value function also approximated by a deep neural network that essentially is predicting or estimating the maximum achievable future rewards that you have discounted by a factor gamma. And what you do in the end to optimize it, you want to minimize the Kullback-Leibler divergence because of our distribution functions between the actor and the critic by training a set of 2 DNNs, deep neural networks, on a set of state, action, and reward tuple state in a replay buffer, which is kind of the memory of the agent. Good. So that was all the theory. Now the fun part. Integrating the custom gym environment. So who has done reinforcement learning for gym environment here? Not that many. Good. Essentially, it's pretty easy. So you have a base class that you need to create, and you need to have 4 methods on that. You need to have an init method that basically defines the action space. So what the agent can do. In this case, it's braking and throttling and steering. Then you have the observation space, which is what the agent can observe. Then you have the step functions. This is the thing that's called 30 times a second, and that performs one action and then returns an observation, a reward, and a done, and some array on the info. Yeah, then I have a reset function at the end of each episode. The agent is being reset to the start-finish line at a certain angle, at a certain speed. And then I have a render function that usually renders the game, but in this case the game renders itself, so it's pretty useless. I just implemented a screenshot, so it can take screenshots in 300 FPS. If you ever need that, it's implemented. And output it as an NumPy array. Good, so implementing the algorithm, so important is I have the action, and that's done by a virtual Xbox 360 controller. Later on, I changed that, so I ditched the controller at the Xbox 360 controller and wrote directly to the game's memory what the agent has to do. Then a reward function. In this case, the reward is the delta in lap completion and the collision penalty. So every step, so 30 times a second, it's measured how much progress the agent makes on a single lap, and that's the reward. The more progress you make, the more reward you get. That's simple logic. Ideally, you would take the lap time as the reward. The lower the lap time, the higher the reward, but that's a very sparse signal because you need hundreds of actions until you would see the reward, and that's not practical. So this is an approximation that you can measure in each step. The observation is kind of telemetry, so speed, acceleration, direction, spin, something that I call a LiDAR, so the distance to the boundaries in 180 degrees ahead in 1 degree steps, and the GPS navigation system, which is kind of the tangent on the optimal racing line for the next 200 meters, because also a human would know what's coming up next. And then I have a done indicator, and that actually tells the agent when the episode is completed, so when the game is over. That's when a lap is completed, a time limit is reached, which here is 3 minutes, and the agent reverses, because when the agent reverses, very stupid things can happen, so I can show that later. Yeah, how do I get to the API? That's also a critical part. There is no game API, as I said, so I need to implement it myself. So even if you would train the agent purely on images, you would need some basic data. So in which lab are you in? Is the lab completed? How much completion did you reach? Also for the reward function. So you need that. And you need to get that in real time. So what I did is, also I used a package, a mod for Need for Speed that allows for windowed mode, more than 5 laps, and it can teleport the car to a given location with a given speed. That's I use for starting location. It has a debug print, which is helpful to find some variables. And then I just built my own API with a very simple strategy. So I open the memory of the game, which is about 300 megabytes. And if I'm looking for the speed, for example, I'm modifying the speed in the game, and then I check which bytes are flipping. So as you can think about it, there are a lot of bytes in memory, so it takes quite some time to figure that out. But there are some efficient tools to do some search. So for example, now it's 100 kph in speed. Then you check for all variables that are 100 at this moment, which is like 3 million probably. Then, you know, you go back to the game, you do it again, then out of this 3 million you see now the value was 100, now it's 120, and you continue doing that. And if you're lucky, after 5 to 6 iterations, you'll get one address or maybe 10, and then you note it down. If you're lucky, actually it's a pointer, so it stays constant when you relaunch the game. If you're unlucky, it's dynamic, and you need to do it all over again, you'll find a byte pattern for it. Yeah? That's more difficult then. And then there's a neat package called PyMem. It's often used for creating cheats, I read. But with PyMem, you can actually read the memory of the game, and it supports byte patterns and jumping to a location in memory and reading from that location. And you can do that in nanoseconds, so it's super fast, actually in real time. And then everything else is calculated in real time in Python, which is a challenge on its own. So there's not a single for loop in my code. It's all streamlined because essentially I have 6 milliseconds to calculate all my feature vector, because I want to be able to train in at least 30 hertz in the end. So I need 30 times to calculate these values, but also 30 times to do a gradient step. And have a quite old computer, so yeah, it takes some time. Yeah, this is the base class to track the x, y, z coordinate and the speed of the car. So once you know the address, that's the difficult part. Once you know the address, it's essentially very easy, because you just note down the address and then you say just read a float from this address. And in this case, I know it's the x, y, z coordinate in the coordinate system of the game at the speed. Coordinate system of the game is measured in meters, pretty nice. So no WGS 84 or something. It's just plain meters, super easy. Yeah, this is the variables that I found and that I'm using. So the easiest ones to find is the XYZ coordinate, because it's displayed on the debug print that you can bring up with extra options, and then you just look out for these variables in memory, find the locations. There's a parameter that's the angle, so that's from 0 to 360 degrees, the Euler angle, so north, west, east, south, how the car is located. It's weirdly a 2-byte integer. Until today, I cannot make sense of that. The values it takes are from 0 to 0 FB12. If you divide it by 0 FB12, you get something, and multiply it by 2 pi, you get something in the range of 0 to 2 pi, and it makes sense, but not sure on that. The speed is stored in meters per second, which is also a float. Acceleration wasn't painful to find, because you don't really see what the acceleration is, and if I stop the game and move out, I don't know if I'm already decelerating or still accelerating. So what I did is I calculated acceleration from the speed trace I had, and then I was checking for variables that flipped in memory, and then I had 10 candidates. I did a correlation analysis, and then I got 3 candidates. It took me 3 nights to figure that out, really. And then I had 3 good candidates and was working really well at the start-finish line, but not in the tunnel. I was like, oh my God, what's going on? Then I was checking that, and turns out that the acceleration value that I get at this address is 2,048 times meters per second squared, sorry. And the sign of the acceleration flips depending on the quadrant you're in the coordinate system of the game. So once you figure that out, it works. Yeah, it took me ages to find that, but now I have it. Then I replaced the angle by signed direction vectors of the car in XYZ direction. How I found that is because a lot of things are going on in this area. So 00938 is a popular address for all these physics constants. And by just looking at that, I could make sense of that, and then just using some trigonometrics, I got that values. Later on, I found spin in radians per second, so angular velocity. I found pitch of the car, so that's up and down, right? Roll of the car, and the lift-off distance, that's the distance from the underfloor to the ground in meters. I found the surface that the car is standing on. These are byte regex because the car is instantiated in the game, so it's not always the same address. And that's an integer from 0 to 5, so 0 is, I think, wood or grass or concrete. Then I have the lab, which lab the car is in, which is also byte regex because it's also instantiated. And I can read the steering and throttle inputs, and later on also write for the Logitech RumblePad 2 controller. Probably you know that was very popular 20 years ago. I still have 2 examples of these. Are not produced anymore, but it's the best controller for the game. Can be fastest with that. The Xbox 360 one I just used because there's a driver for that. Good. Having the XYZ coordinate, I can map the track. So I was driving myself, then I could map the track. So the colorful line is the racing line I was using myself. And the boundaries, then I needed to get the boundaries. In order to calculate something, I needed to get the boundaries. There was no easy way, so what I did, I'm not stupid. I was real-time mapping the XYZ coordinate. And then I took 10 minutes and I was going on the left border. And then I was going on the right border. And then I had mapped the track. Yeah. What I then did is I saved all of that in a data file. I run that with higher frame rate. So I had, I don't know, 10,000 points for the left boundary and 10,000 points for the right boundary. And the algorithm that's used most in the game is actually tree-based nearest neighbors, because whenever I have in real time the XYZ coordinate of the car, and I want to know where the next boundary is, I check where it is on the main trajectory, I check where it is on the boundaries on the left-hand side and the right-hand side, and take the ones that are in front of the car, and then I calculate all vectors back to the car, I determine the angle it is, I discretize it, and then I have the LiDAR in front of it. And KD trees is super fast, works also in nanoseconds. Awesome, yeah? So I have everything ready to do the actual training, except for the features. For the features, I thought, okay, I need to give some vision to the car. And I need to give some navigation. So here's a screenshot from the game, and this car here is standing in a left corner. Yeah, you can see it on the minimap here. There's a left corner coming up. And then I was calculating this LiDAR. So in 180 degrees ahead, what's the maximum distance to the nearest border? And a navigation, which is the tangent on the racing line and the angle that it forms with the coordinate system. That's the feature. That's actually the vision that the agent has in the end. Yeah, if you plot that, it looks like that. Beautiful ggplot2 graphs, yeah, much better than in Python, by the way, still. So on the left-hand side, it's the LiDAR. It's 180 lines, and you see the distance in front. So here you can see it's a left corner, yeah, because it's clearly visible. And on the right-hand side, you have the GPS navigation system, and that's basically an angle that I have computed, yeah, the tangent to the racing line. Good. Some demo time. So I got all this telemetry, and to show you that it works in real time, this is an example. The overlay here is just from the Python console, and you can see when I'm driving here myself, you see the XYZ coordinate here on top, you see the angle, the Euler angle, you see speed, here's the acceleration, and that's why it's really hard to find that, because it can change really quickly. You have the spin of the car, the surface, it's here, in this case it's asphalt, the lap completion, in this case 7% of the lap completed, and then you have the LiDAR. Here it's only 3 values, 60 degrees to the left, so here it's 10 meters, straight onwards, 160 meters, and to the right, 40 meters. Yeah? And it works with every camera perspective, works with any weather, works with any car, super invariant to what you do in the game. Nice. Now I have that. I'm going to skip that, but that's some functions that I have in the API, so I can return the vehicle telemetry, the LiDAR, collision, if it collides with a boundary, so whenever it's closer to a delta, to a border, say it's a collision. Yeah, some other stuff on the lap and lap completion that I can calculate. So for my reward function, I need how much lap completion is achieved between 2 steps, and I can calculate it with the KD tree and the nearest neighbors calculation easily. And then I can reset the vehicle. Yeah, so since I want to do a hot lap, when I reset the vehicle, it starts at the start-finish line at a certain angle at a given speed, so I have always the same conditions. And I can take the screenshot, yeah, as before. Good, virtual gamepad. In this case, if you use the vGamepad library, it's a wrapper for vGAM, so virtual gamepad emulation framework, and the signal is continuous between -1 and +1, and essentially the x-axis of the left stick is steering, left to right, and the y-axis of the right stick is throttle and brake. Good. You can also directly write it to the game. It's a function that I wrote. Actually, you man in the middle attack the game, kind of. So you block the real controller inputs and write your own controller inputs to that. So you go into the assembly code, write a no instruction into that it blocks the controller, and then you write your value to that, which is a 2-byte value. Yeah, found that. It's not making making things any faster, but it's possible. If you want to do it via keyboard, it's also implemented, but it's just slow because you have binary options for full left, full right, full throttle. It's not fast. Don't try it. Doesn't make sense. Good. Then, yeah, the action is done via this Xbox 360 controller. It's from -1 to +1, so every value is possible. Full left, full right, everything in between. 0 would be nothing in steering. And for acceleration, only 3 values really make sense. So -0.4 is full brake, but not reverse. 0.7 is half throttle, and 1.0 is full throttle. So game is called Need for Speed, so 99% of the time it's full throttle. So anyway, so you can leave out this discretization, actually, but then the agent just takes ages to figure out if it should give 98% speed or 100% speed, so it's not really beneficial. So it's simplified. The reward is the delta in lab completion, and penalty is optional. So actually there's a legit strategy in the game to bang against walls and lose some speed and then get the corner optimally. It's possible, the agent also does that without the collision penalty, but the other way is kind of nicer, so I implemented a collision penalty. Yeah, in this case, if you would choose a high enough discount factor for future rewards, it's kind of approximating the lab time minimization criteria that you really want. Yeah, typical reward is 0.00035 if you play in 30 Hertz. If you play in 60 Hertz, your reward changes to half of that. Problematic for the implementation, I can tell you. Good. Some fun with reward functions to check if you're still awake. So I brought some examples what can go wrong because it's very sensitive on these reward functions. So the first one here, I implemented the algorithm and I used a different reward, and then I was seeing this. So agent starts, and then it engages in burnouts endlessly. I was like, weird, right? Can you guess what the reward function for that was? Anyone? An idea?
Only entropy?
Yeah, could be. No? No, that's later on relevant. That's actually speed. If you say, hey, I don't want to implement all that stuff, speed is easy to measure, I just give it speed. What it does then, it does burnouts because essentially the episode never ends. So it goes infinitely long, and if you do a burnout, you never crash. You always do something, so you're always 20 plus 28 kph and infinite reward. Yeah, it's the right solution, yeah, but you don't want that. The second one here, and then I stop with that one, I saw this pattern. So the car was starting, was going on, and suddenly it was turning around, and it was going reverse over start-finish line. It's like, weird, something must be wrong. Yeah, but that was when I had delta in lab completion, but without blocking it to go reverse. Because what then happens is, maximum reward is what you get when you cross reversely over the finish line, because you're at 0% lab completion, and suddenly you're at 100% lab completion. So maximum you can get. To fix that, I just blocked the car from reversing. Easy. And the third one is also simple. So if you set a collision penalty, and you set the collision penalty too high, this happens. So the agent learns, living is very painful. I rather do nothing because then I cannot get punished, and then it just stands still after some iterations. So it's really difficult to get that right. Good. The observation is again this LiDAR and GPS navigation system. So that's a vector of 594 components with the telemetry, the LiDAR, a collision indicator if the vehicle is reversing indicator, the inverse lap radii ahead, the lap angles ahead, and the last 5 steering inputs. And yeah, comparing that with an image, that's 500 times less amount of data and not that noise. And you can use it in different camera perspective. You can use it if there's rain in the game. All that works. And you can calculate all that stuff in 8 milliseconds, even on my 10-year-old PC. And the done indicator is just lap time completion time limit or reverse. Yeah, then it's game over. Good. That's actually the whole code to make it run once you have the API, so pretty easy. You import the packages, of course, then you instantiate the virtual gamepad before the game. It appears as a Xbox 360 controller in the game. Then you create the environment, once you have that. Then you run the model, so here it's a soft actor critic with MLP policy, which is a fancy word for fully connected deep neural network. You give it the environment that you have, set gamma, so the discount factor to 0.99, set a seed for reproducibility, and the buffer size is just the maximum that fits in 8 gigabytes of VRAM while running the game at the same time and running on Windows. Good. And then I have some callbacks here that do some logging because the game randomly crashes, which sucks, because then my replay buffer is lost and I need to restart everything, and the game has a time bug, so the timing in the game gets really wrong after you're playing the game for 5 hours by 1, 5, 10 seconds, so I time externally. Yeah, and GPU training in real time on my old gaming PC takes about 24 hours, so I have a Xeon E3, which is a 4th gen Intel Core processor, so it's really 10 years old, and a GeForce GTX 1070 graphics card with 8 gigabytes of VRAM. Good, finally, time to come to an end and to show the final results. So this is the final result, going to walk you through it. I did some advancements recently, so it's more than a second faster now, but the quality of it doesn't change. So here you see the controller. This is what the agent does. So the agent really finds the racing line. It doesn't collide with anything. It's very stable. Even if you throw it to a boundary, if you break it or it crashes, it finds back to the racing line. It completes the lap every single time. It finds the right way to the entrance to the tunnel, the right way to exit the tunnel. Doesn't crash here. You see it's a little bit jittering, and that's a problem, but it's pretty fast. Here it's the same line that I would do, but later on it chooses a little bit of a different line. So here it follows through to the easy part. Here it doesn't go to the right, weirdly. It stays on the inside line because it's, I don't know, shorter, but it's not faster, I think. Crosses down here, and then here on what's also different, here it stays on the right-hand side, not the left-hand side. That's doable. Also some pro player did this in the time. That's just a different line, but it's equally fast. And then it continues. It goes over the start-finish line in a second, and my current best time is a 1 minute 8:30, so it's 1.5 seconds off, but still pretty good. So I started from scratch, no imitation landing, no nothing, no inputs, no training. Good. Here two comparisons. So I said I can do it with a collision panel and without. So in this case, it's without the collision penalty, and the only difference you see, if you go to the tunnel, you can either brake or you can do what the agent does, hit the wall, and then continue. Both is equally fast. The left-hand side for a human is just very difficult to achieve consistently. So on the right-hand side is what you see before. Just don't crash to the boundary. Use the brake instead. Yeah, here. That's the better way to do it. Good. That's kind of it. Some more slides. Some notes. So it generalizes well to other cars, but not to other tracks. So you can give it another car. In this case, I'm just talking, but this is the Porsche Carrera GT, which is equally fast on the same track. You can do the same lap times with it. And you see, it also steers it without any retraining. It has never driven the car. It's very different to drive this car, but it also works. In this case, it could collide once because it doesn't know that this car is much wider than the Lotus. It's just not in the data. It's very stable in lap times. And just fast forward here a little bit. And you see it does a 110, so it's one or 2 seconds slower, but not by a big margin. It doesn't completely go off. You can train it on another track, but without retraining, if there comes a corner that has grass, it totally drifts off because it had never seen grass before and doesn't know it's slippery. Or if there's a 90-degree turn and you need to brake really hard, it also doesn't work. But for other cars, it works with any car in the game, and it obliterates the competition in the AI that the game has, actually. So it's really fast. Good, some comparison. So that's the training progress that you see over 24 hours, more or less. So it starts off. There's a point where it starts, and then it completes the lap for the first time, and then it continues to always complete the lap. There's some spikes because the game crashed and I needed to refill the replay buffer. But yeah, just to compare it. So the in-game AI does a 133.17 on hard, yeah? Just to give a perspective. The casual gamer would probably do a 118, a good gamer 110, pro gamer 19. So if you would do a 1.8 that the AI now does, you would have won every match in the Electronic Sports League. Probably only not against the top 5. And yeah, the world record here at 1 minute 6 is more like a 1 in a million lap that you can achieve. Good, conclusion. Modeling is difficult, also to keep the Markov property because the game is running in real time and I have no control over the game. So I just need to make sure that my stuff also runs consistently. What helps against jitter is setting vsync for the game because then the frame rate of the game is constant and the update there. Some features are noisy, like the LiDAR, because I just calculate from the data I have, and it's discrete. Works well, achieves a really good lap time. It's also very stable. It's accessible, so it runs on my old gaming PC, and it's comparably fast. It takes 24 hours. It's a good heating in the winter. I probably run it 100 experiments or so, like dozens of hours. Quite nice heating. But it's also comparably fast. If you compare with the Sony paper, in the first they say they reach superhuman performance after 73 hours, but they use 80 cars in parallel on 4 PS4s. And on the second Sony paper, they do a little bit more, to be honest, also some strategies on overtaking, but they use 1,000 PS4s in parallel and 80 cars on each, so kind of they're brute forcing the whole space, so to say, and generalizes very well to other cars, but not really to other tracks. Good, thank you for your attention at this late time, and yeah, time for some questions.